In this session, we get to answer this question about projectiles. A body is thrown from the top of a tower, 30.4 meters high, with a velocity of 24 meters per second at an elevation of 30 degrees above the horizontal. Find the horizontal distance from the roof of the tower to the point where it hits the ground. We need to find the horizontal distance. First step is to always get a diagrammatic view of the question. So, a body is thrown from the top of a tower. So this is the tower. We have a body right there, and this body is being thrown from the top of the tower, like that. So the tower is 30.4 meters high. So this is 30.4. It's 30.4 meters high with a velocity of 24 meters per second. So the velocity with which this thing is being thrown, u, is equal to 24 meters per second at an elevation of 30 degrees above the horizontal. So meaning the elevation, the angle of elevation here is 30 degrees. Let me write it there. So the angle of elevation there is 30 degrees above the horizontal. Find the horizontal distance from the roof of the tower to the point where it hits, the ground. This is the tower, and right down here, this is our ground right there, and they want us to find the horizontal distance. So the horizontal distance is the distance from the roof to where it hits the ground. This is where it hits the ground. They want us to find this horizontal distance right there. So unlike the numbers we've been doing previously in our previous sessions, you find that this is a bit different. The ones we've been doing previously, the particle starts from the same ground level and it goes up and comes back down on the same ground level. And in this, but for here, the point of projection is on top of a tower. However, it is moving up to down there. So they want us to find the horizontal distance from the point where it is projecting up to where the thing ends. Yeah, find the horizontal distance from the roof, from the roof, the horizontal distance to where it drops. That's the distance they're talking about. Okay, so just one thing that we need to know with this. Now, if you look at this is a bit irregular. So with this, it is we can't apply the formulas that we've derived before. Now, the formulas that we have derived before will only apply when we are dealing with perfect conditions. By perfect conditions, I mean a projectile starts from the same ground level, it goes up and it comes down on the same ground level. That's when we can apply the formula for horizontal range, for maximum height, and the time of flight. We can apply them. But this is not a perfect condition. This condition here you're seeing, it's like this. This is the platform where we started from. It moved up a bit. Then on coming down, it exceeded. In other words, the trajectory went and exceeded where it stopped, and it dropped somewhere down here. And so it means that we need to apply first principles. We are supposed to interpret it from first principles to be able to get what they need from us. When we are using the formula, when we are asking for maximum range, when we want to find the time for maximum range, we simply apply the other formula we derived to find the time for maximum range. But in this case, we are being required to find some extra distance. There is this time for maximum range, then there is this extra distance here from this point up to where it lands. That is what we are talking about here. In other words, here, our point of projection is this. This is the point of projection. But this falls way beyond and goes down here, and we need to find this distance. Now, this is not as perfect as this is. So it means we are going to do this using one of the three equations of motion, and we are going to do it from first principles. Now, this is one thing that you need to know, that when this particle is at this point, its displacement is 0. If it is moving upward, its displacement is a positive one. If it is moving downwards, its displacement is a negative one, that is if it is below this line. So in other words, as this particle keeps its displacement from this position as it's here, its displacement is in the positive direction. Okay, So when it comes here and it moves down, its displacement is negative as long as it's below this line. Now I'm trying to explain this, but if you've already covered the difference between distance and displacement, I expect that you should have covered that by the time you're doing this topic, and so you should be in position to understand perfectly what I mean as I explain this displacement thing. I'm only saying it for some of us that might not be understanding what's going on. So let's get back to this diagram here. We are required to find this distance. Again, it's just about playing around with the equations of motion. We talked about those equations of motion in our previous session, and here they are. This. So just look at these three equations of motion and ask yourself, which of these three equations of motion is most likely to give you what you want? They want us to find the horizontal distance. But then at the horizontal distance, from the point of projection, we know that this point here is like our zero ground, our ground zero. If I'm to be displaced up, my displacement up will be a positive one. My displacement downwards is going to be a negative one. And we know that by the time this particle moves from this point to come and land on this ground, remember, our zero level is the level where the projection starts from. If the projection was starting from the ground, this would be our zero level. When the projection starts from here, it means now this is our zero level. And so if this projection is falling below the zero level, it means it is being displaced in the negative sense. However, we know that its displacement is negative. Why? Negative 30.4. Because this tower is 30.4 meters tall, it means this point, it moved up, positive displacement, then it came down and it went downwards to the ground by 30.4 meters down. In other words, 30.4, it is its displacement at the time it hits the ground is 30.4 meters. That is its displacement in the y direction, or in the vertical direction. So what do they want? Let's get back to our diagram here. They want the horizontal distance. The horizontal distance from the roof of the tower to the point where it hits the ground. This is the distance they want. Let's call that distance m. That's the distance they want you to find. Now, this is the horizontal distance that they want. And we know that this distance is given by speed times time. That's the distance given. That's the distance. Distance is speed times time. So, looking at the distance, yeah, we are looking at distance in the x direction. We are looking at horizontal distance. We are not looking at the vertical distance. The vertical distance would be this displacement, but here it is that. So it means that find the distance, we need the speed, and in this case, the speed we are going to we are supposed to resolve this speed in the horizontal direction. So it means that the distance here is going to be equal to the speed, which is going to be u times the u cosine of 24. This u times cosine of 24 is the distance in the horizontal direction. Multiply that by the time. Now we do not know the time, but we need to know the time covered as this particle moves from here up to there. So the speed has been, it is u cosine of 24. Remember, we're doing this from first principles using the equations of motion. So u cos that times time. Now the time is what we're supposed to find using the equations of motion. So like I have explained earlier, when you look at s is equal to ut plus a half at squared, and you look at this, you find that the displacement here is negative 30.4. This particle falls below the zero level by negative 30.4. So meaning our value of s here will be negative 30.4. So when you plug it in here, we will be able to get the time. We will be getting two values of t. Two values of t, and we shall choose one of them that applies to when the particle drops at this level. So let's first find the value of t. When we get the value of t, then we shall come back and plug it in here, and then we shall go ahead and get the distance, this value of m. So let's get to it. So we know that S is equal to UT plus a half AT squared. We are using this from first principles. What is the displacement S? The displacement is in the negative sense. In this case, it is negative 30.4. So we shall say this is negative 30.4. So negative 30.4 is given by UT. Now the UT, in this case, remember we're doing this from first principles. So, and this is S in the Y direction. So because it is in the Y direction, it means you're supposed to resolve this initial velocity in the Y direction. So it's going to be U sine of 24 times the time. Then it's going to become plus a half times acceleration, since it is going upward here, it's against gravity, times negative g t squared, like that. So this all becomes negative 30.4 is equal to u. Our u is 24, so it's 24. Oh, this is supposed to be sine of 30. The degrees, it is 30 degrees. The theta, value of theta is 30. So it's 24 sine of 30 times t. That is going to be minus a half times the gravity, which is going to become 9.81 times t squared. So when we simplify this further, this is what we come up with. This is 12t, and this is 4.9t squared. We rearrange this to form a quadratic equation, as you can see. So if this is if we rearrange this to make it a quadratic equation, this is going to become 4.9t squared. We are pushing everything on one side. So this becomes 4.9t squared minus 12t minus 30.4 is equal to 0. That's a quadratic equation right there. So when you solve this quadratic equation, punch it in your calculator or use the quadratic formula. You'll end up with two values of t. One of the value of t is 4. Another value of t is 1.5. So of these two values of t, this is negative 1.5. So of these two values of t, which one are you going to choose? Now these are the two values of t we are getting when the displacement is negative 30.4. In other words, at negative 30.4, the displacement, if I'm to complete this curve, this is what this means. If I'm to redraw it here again, this is our tower. We hit something here and it came like that up to there. At this ground, this is 30.4. This is the zero ground, zero level. So this is more like an extension right there. We can extend this graph arbitrarily up to this 30.4. So what this means is that this value of t is equal to negative 1.5. This is the value of t here, negative 1.5. If we are to extrapolate this thing to up to there. And then this second value of t, 4, is the value of t at that point. So between the two, we are interested in the time taken for this particle to hit at this point, not at that point. And besides, we even negative 1.5 as a negative time is not realistic. So we take the higher value here, which is 4 seconds. So it means our value of t here is 4 seconds. It's the one where it's the value of the time taken for the particle to move from that point to come up to there. In meaning it's the time taken to move from here to there to cover this horizontal distance. So our value of t is 4. It's what we are going to take. Now that our value of t is 4, now we can come back to our initial formula here and complete and answer the question as it is required. So here it's going to become distance is speed times time, which is u cos 24 times t. This is the same as saying u is 24 meters per second, so it's 24 times the cosine of Actually, this is supposed to be 30. I'm sorry. The angle there is 30. So it's u cosine of 30. Multiply that by the time. The time here is 4 seconds. And the answer we get, it's 83.138 meters. So that is the distance here. And so with that, we are able to answer that question. This brings us to the end of this session. Thanks for watching. In our next session, we get to do yet another worked example on projectile motion. Don't forget to share this video with your friends. My name is Arnold Ranga Kuramia. This is Kisembo Academy. Take care.